Dry friction. So here is our learning outcome. Understand and apply characteristics of dry friction. So surfaces provide friction forces tangent to the surface to resist sliding. So an advantage is people walk without slidings, brakes on cars to stop the vehicles. And some disadvantages include that it produces unnecessary heat and that it's difficult to slide a heavy box across the floor. So dry friction refers to the friction that exists between two rough solid surfaces. So first we have static friction. If there is no relative motion between two surfaces that are in contact, the normal force and the friction satisfy the following relationship, where Fs is the limiting static frictional force. Fmax is the maximum static friction force that can exist between the contacting surfaces. Mu(s) is the coefficient of static friction, and this is an experimental constant that depends on the composition and toughness of the contacting surfaces. The direction of friction always opposes sliding. Next is the verge of sliding. When the surface areas on the verge of sliding, so F is equal to Fmax, which is equal to mu(s) times n, the surfaces are at rest relative to each other. However, any change that would require an increase in the friction force would cause sliding. Dynamic friction. If the two contact surfaces are sliding relative to each other, F is less than or equal to Fk. So Fk is the kinetic or dynamic friction, and μk is the coefficient of kinetic friction. So in the graph, we can see that Fm is the static frictional force, and Fk is the kinetic frictional force. So in the graph, we can see that as P increases, the static friction force F increases as well until it reaches a maximum value of Fm. The maximum static frictional force that can be developed is independent of the area of contact between the surfaces, provided that the normal pressure, P, is not very low nor great enough to severely deform or crush the surfaces between the bodies. The maximum static frictional force is generally greater than the kinetic frictional force for any two surfaces of contact. However, if one of the bodies is moving with a very low velocity over the surface of another, Fk becomes approximately equal to Fs. When slipping at the surface of contact is about to occur, the maximum static frictional force is proportional to the normal force. When slipping at the surface of contact is occurring, the kinetic frictional force is proportional to the normal force. So here's our example. The uniform crate shown in the figure has a mass of 20 kilograms. If a force P is equal to 80 newtons is applied to the crate, determine if it remains in equilibrium. The coefficient of static friction is 0.3. So to solve this, we first start out with our free body diagram. So as shown, the resultant normal force NC must act at a distance x from the crate's center line in order to counteract the tipping effect caused by P. There are three unknowns, F, NC, and x, which can be determined strictly from the three equations of equilibrium. So using the equations of equilibrium, we first solve for the forces in the x direction. By taking the summation of forces in the x direction, we solve for F. Next, by taking the summation of forces in the y direction, we can solve for NC. And now, by taking the moments about point O, we can solve for x. So solving, we have F is equal to 69.3 newtons, and C is equal to 236.2 newtons, and x is equal to negative 9.08 millimeters. So since x is negative, it indicates that the resultant normal force acts slightly to the left of the crate's center line. Also, the maximum frictional force, which can be developed at the surface of contact, is Fmax is equal to the coefficient of static times NC, which is equal to 70.9 newtons. Since F is less than Fmax, the crate will not slip, although it is very close to doing so. So in summary, we drew out our free body diagram and we solved for F, NC, and X, which helped us solve for F max. And since F is less than F max, the crate will not slip, although it is very close to doing so.